Okay, thank you for coming and your interest in TALP and DLB. So I'll start giving an overview of what's the DLB library, although in the presentation today we will focus on the TALP module. So the DLB library is a dynamic library that started for helping load balance MPI applications, and that's the main module of the DLB library. The LeWI module takes care of doing this load balance between MPI processes of an application that has unbalance. We have another module that is DROM that is used for doing more coarse grain resource management between MPI processes also. And then the last module that was added that it's TALP, that it's for performance measurements. We will today focus on this module. The nice thing is that they are all integrated in the same library. They can collaborate. The different modules work together well, but they are independent. So you can enable one module without the other. And they share the same infrastructure, the same shared memory, and the APIs. So as I said, we are focusing on the TALP module. The TALP module is a profiling tool that provides low overhead. This means that we can use it for production runs, so you can get it on your big execution and it won't add any overhead. It reports pop metrics, and it can be used transparent to the application so that we can run without problems with anything. But it also provides an API to obtain metrics at runtime or to annotate the code in case you want to get metrics for specific regions of the code. The current version that I'm presenting today is version 3.6.0 beta. We call it beta because we have added in this version all the GPU metrics, and this is what I will focus in today's presentation because it's the new thing in TALP in this version. Although it has been tested, we have tried with different applications and benchmarks and so on. We call it beta because there are no users that have used it yet. But in principle, it's stable and can be used. The current version, it collects MPI efficiency metrics, it collects hardware counters, OpenMP metrics. It also has support for the TALP pages that it's useful for CI/CD integration, and the new thing that I'm presenting today, the GPU efficiency metrics for NVIDIA devices. The work that we are doing now that will be ready in the following weeks or months is to add also GPU efficiency metrics for AMD devices, GPU computational metrics, and also offer support with TALP pages for the GPU metrics that right now are not supported. So why, let me ask this question that some of you may have now, is why we need yet another profiling tool with all the ones that we have in the wall. The nice thing about TALP is that it's not a profiling tool. So although we sell it like that because it's what people usually say, but we give efficiency metrics, not profiling information of the time that we spend in the different MPI calls. And this is a problem that can be seen in this example, where you have an application that has a load imbalance between the two MPI processes. One process have more work than the other, and the first one needs to wait for the second one to finish. You have another application where both processes have the same balance, but they have a lot of MPI calls. A profiler will tell you that there's a lot of time that your application is spending in MPI, but without more information on which is the real issue. While TALP will report you that application A has a problem with load balance, while application B has a problem with communication efficiency. And this is why the metrics that we report in TALP are so important. And that is why I'm going to spend several slides talking about which metrics we are capturing, what do they mean, and how we compute them. This is the original set of MPI POP metrics that come from the POP Center of Excellence that were originally defined. It's a hierarchy of metrics. The green ones are efficiency metrics, while the blue ones are scalability metrics. This means that the green ones can be computed by their own in any case, and the blue ones need a base case to be computed. So we compute, we have several runs, and then we compute the blue ones in base the first one. All the child metrics are the product of all the parents are the product of their child. And then when we implemented these metrics inside TALP, there are several things that we could not have. For example, we cannot divide between serialization and transfer because we need simulation to do this. So the metrics in gray are not computed in TALP. But on the other hand, we added two new metrics that help us tell if the load imbalance is happening inside the node or outside the node. Regarding the scalability metrics, as I said, we need several runs. As TALP is giving you the metrics for a single run, then we cannot compute them. But it's true that TALP offers enough information for the user to compute these metrics by hand when they have several runs obtained with TALP. So you get one execution with TALP, you get the number of instructions, you get another execution with TALP, and you also get the number of instructions, so you can compute, in fact, the instruction scalability on your own with this information, although we are not able to provide it because we are just reporting metrics for one run. So how have we extended this model to also measure GPU efficiency metrics? In these presentations, I'm going to use GPU or device and CPU or host. So you will see that we label the metrics as host or device, but sometimes in the titles I also use GPUs because it's widely used. So the first decision that we took is to have two separate models for the host and for the device. And these two metrics are not multiplied between them. They are completely independent. So for the part of the host metrics, the host metrics were the ones original from that I was presenting before that were from POP. What we have done, we have added an additional metric that is the host parallel efficiency that accounts both for the MPI parallel efficiency and the device of load efficiency. The device of load efficiency is the new metric that we have added in the host side of the metrics to tell us how much time we are using in the host because using the device. In the device side, the device metrics will tell us how well we are using the devices, the GPUs in this case. And this is the tree of metrics that we defined. The device global efficiency is divided between parallel efficiency and computation, similar to what we have in the host. So we have the parallel and the computation. In this case, the computation efficiency or scalability is not clear yet. It's not defined yet. So this is work in progress. This is what we are working now on doing. And what I will present today is these ones that are in red. So the device parallel efficiency will tell us how much time we are using the device for doing useful work. And when I'm not using the device for doing useful work, how much time is lost because I'm moving data, the communication efficiency, how much time I'm losing because the devices are not balanced the same, one has more work than the others. And the orchestration efficiency tells us how much time is being lost because the device doesn't have enough work to do. So there's a kind of a scheduling issue where it's not getting enough work to compute. So to summarize, we have the host and device efficiency that are unrelated to different trees now. We measure them separately, but as you will see now, we interpret them together. So when we see the metrics, it's important to interpret them together. The device global efficiency is divided in the device parallel efficiency and the computation efficiency. That is still work in progress. We consider one GPU as a single resource. So when we talk about the device efficiency, one GPU is one resource. We don't take into account the streams or anything else that is inside the GPU. This will be accounted in the computation scalability or efficiency. And the same way that the original POP MPI parallel efficiency metrics, all the arrows, all the relationships are multiplicative. So all the product of the child are the parent for the two trees. How do we compute these metrics? I'm going to explain a bit what we do to compute each one of these metrics, and then what they mean and how they apply to different use cases. So to compute the original MPI POP metrics, what we did was to classify the states of the processes in two states. So if this is an execution, we have 4 MPI processes. You see the 4 lines. This is the time. And we classify the status in useful, blue, or not useful. Either the process is doing useful work or it's not doing useful work. Usually not useful corresponds to MPI, but could be other things that were not MPI, that were not useful. One process is always corresponds to one core, and one core is the resource unit. So that's where we compute the efficiency for the different resource units. In this definition of the states, we define C as the useful time of the process, T as the total elapsed time, and P as the number of processes. With this information, then the parallel efficiency is computed as adding all the useful duration divided by the total time multiplied by the number of processes. This is giving us how much time I'm using the resources to do useful work. The load balance is computed aggregating the useful time per process. So we have the same use case, and what we do is we add all the useful time of each process, we compute the maximum, and then based on this we say, okay, everything else that is because this guy is more loaded than the others is because load balance. So the formula is like this, and it's the ratio between the useful, the sum of the useful of all the processes divided by the maximum process, process that was more loaded multiplied by the number of resources. The communication efficiency is, once we have the load balance computed, then the time that the most loaded process was spending in not useful, so the remaining time, and can be computed like the maximum compute time divided by the total time. So now, on top of this, this is where the classical MPI POP efficiency metrics, on top of this, we are computing the GPU metrics. How we do this? For this, we need more states. So now, instead of 2 states, we will have 3 states for the host and 3 states for the device. The host will have the useful, as we had before, the not useful that now we call MPI. So the time that I'm inside MPI calls is MPI. And then the third state is the waiting for GPU. And in this state, I account for any time that the host is inside what we would say in the CUDA runtime. This means I am either launching kernels, I'm waiting for data from the GPU, I'm sending data to the GPU, anything that means that the host is waiting for an answer from the device. The devices are also divided in 3 different states. They are either doing useful work or they moving data. Data movement can be between GPUs, can be between GPU and CPU, or CPU and GPU. So any moment where the GPU is busy just because it's moving data instead of being computing things, it's data transfer state. And all the other time that the GPU or the device doesn't have anything useful to compute, we consider idle. In case, so as I said, we consider the GPU as a single resource. In case that one stream is computing and another stream is moving data, we assume that that GPU is doing useful work, so it will be counted as useful. So how do we compute the different metrics? Now that we have defined the states, we have the host metrics have changed a bit because we have added one state. So the parallel efficiency is computed as before. We add all the useful time and divide it by the total time. and this still gives us how much time I'm using the resources to do useful work. To compute the MPI parallel efficiency, we consider the waiting for the GPU state as useful. So from the point of view of the process and the MPI communication, the waiting for the GPU is useful time. So the MPI parallel efficiency is adding the useful time plus the waiting for GPU divided by the total. And then the device offload efficiency, that is the time that the host is using to offload work to the GPU, is computed as the total useful time divided by the useful time plus the time that I'm wasting offloading work to the GPU. This device offload efficiency quantifies how much time the resources are idle. In this case, we are in the host metric, so the resources are the CPUs. How much time the CPUs are idle due to the fact that they are using devices. Now we move to the device side of the metrics. So to compute the device parallel efficiency, we also have like the 3 GPUs and the 3 states. So the parallel efficiency is still the useful time divided by the total time. So I add all the useful time of all the devices and divide it by the total time. And this is the time that the CPUs are used for doing useful work. The device load balance. So we will do again the same as we do in the host. We add all the useful time, we compute the maximum, and the difference between the maximum and the maximum multiplied by the total number of resources and the total useful time is the load balance. This tells us how much time is being lost because one device has more time is more time doing useful work than the others. The communication efficiency, then we aggregate also the data movement times, and the process that is more time doing useful and data movements is the one that is limiting us. So all the ratio between the useful time and the maximum useful time plus the data movement is the communication efficiency. This is the time that I'm waiting for the device to move data, that if the data movement was instantaneous, this time would be reduced and be 0. And the orchestration efficiency, this is, yes, the orchestration efficiency is the time that the GPUs are idle because they don't have work to do. So at the beginning they were computing, then they were moving data, and this time is because they don't have anything else to do. So we compute it as the ratio between the maximum of the useful and the data movement divided by the total time. And this metric tells us how much time the devices are idle because they don't have pending work to do, either because the CPU has not offloaded enough work or because there are dependencies between the kernels that are and cannot be executed. So here, just to recap, is a summary of the new metrics that have been added in TALP, what they mean, and a low efficiency, how we can interpret it. And now I am going to share some examples. So what we have done here is that we have a synthetic benchmark that we can tune to offload more or less work to the GPU, to do more or less work on the CPU, to move more or less data. With this very simple benchmark, we are able to provide different patterns or use cases that we can then check how the metrics look like. And we use it to check that the metrics are meaningful and correct. So I'm going to share several to show you how an application with this issue, which kind of metrics will obtain. In this case, the first one is a typical GPU application, let's say, where most of the work is offloaded to the GPU. The work of the CPUs is well balanced, And the GPUs are also well balanced. This is the execution trace of this benchmark. Blue means computing. Orange means that I'm waiting for the GPU. And we see here that we have two MPI processes. This is the process and this is its GPU. So we have two processes, each one with one GPU. And in the GPU line, you see the same. So the blue means that the GPU is doing useful work. Gray means that it's idle, that it doesn't have work to compute. The metrics that we obtain for this use case are these ones. And from analyzing these metrics, what we see is, okay, we see a low offload efficiency for the host that indicates that the CPUs are only used for offloading work to the GPUs. So the CPUs are not used for doing useful work. On the other hand, the parallel efficiency of the device is quite high. In general, all the metrics are quite high. This indicates that the device is being used efficiently. That is the case that we are seeing. The GPUs most of the time are busy, and the only time that they are idle is because they don't have more work to do from the host, and this is notated here in the orchestration efficiency. The second use case is the other way. So we have a few work offloaded to the GPU. This is an application that is not so well ported to GPUs. Still, the CPUs are well balanced and the GPUs are also well balanced between them. This is the trace of this execution, and the metrics that we obtain in this case, the host metrics are high. The parallel metrics of the host are high because the host, the processes, most of the time are doing useful work, and in the device they are very low because the device most of the time is just waiting for the host to offload work to them. So and the metric that is telling us is the orchestration efficiency. So we see that in the device, all the metrics have, so load balance is good, the communication efficiency is good, but the orchestration efficiency is low because there's no work offloaded from the CPUs to the GPUs. In this case, we started introducing some load imbalance, and there's imbalance between the GPUs, but the CPUs are well balanced. What we see now is we see a low MPI load balance because although the CPU part, the load of the CPU part is well balanced, as for the MPI, the offloading is counted as useful, there's some work that is imbalanced at the CPU level. So there's more work in one of the processes, and that's why the MPI parallel efficiency is low. We also see a low device offload efficiency because while the CPUs are waiting for the GPUs, they are not doing anything. So all this time, it's time that it's lost due to being waiting for the GPUs. And in the case of the device, also the parallel efficiency is quite low because just one of the GPUs is working because the load is almost in one of them and the other one has very few load. So this is seen here in the load balance. We see a low load balance in the device. And the others are more or less okay. The orchestration is 82 because for some time the GPUs are waiting for the host to offload work. In this case, it's the other way. So the GPUs are well balanced. So that you can see that in the trace, the CPUs have the same amount of work, while the CPUs are unbalanced. So the MPI process 1 has more work than the MPI process 2. What the metrics indicate us that there's load balance, MPI load imbalance here. That is because there's load imbalance. There's also a low device offload efficiency because the CPUs are not being used while waiting for the GPUs. And we also see a low orchestration efficiency because the device is waiting a lot of time for the CPU to offload work to it because it doesn't have any kernel to execute. In this case, both the GPU and the CPU is unbalanced. And now we see that the low MPI load balance indicates us this. And we also see a low of load efficiency because the CPU is not overlapping work with the waiting for the GPU. And we also see a low parallel efficiency for the device, that is mostly because the load imbalance and the orchestration. So in the difference between these two cases, you can see that the device in the previous one for the load balance for the device was 1, while here it's 0.5. And in the last case that we have added the green is data movements in the GPU. So all this time there's data being moved between the CPU and the GPU, and the metrics look like this. So we still see some load imbalance at the MPI level. This is because, in fact, the MPI process one, it has more work to do in the sense that has more data to send. So there's that's why the host shows some load imbalance. There's also a low of load efficiency in the host because most of the time we are waiting just for the GPU to come back or to send data to the GPU. And the device parallel efficiency is quite low also, but in this case we see that it has a good load balance, and what the metric that is low is the communication efficiency. So these are very simple use cases of applying the GPU metrics, but helped us see that we can identify the different patterns that we can find in one application. I didn't have time to add it here, but we tested it also with different, with real applications, and the metrics were also relevant and helped us understand how the application was performing. So now I have explained a bit how the metrics are computed. I have shown what they represent and how from the metrics we can understand which is the performance or which are the bottlenecks of an execution. And now I'm going to show you some TALP use cases because this is a bit what I've been presenting up to now seems a bit abstract, and I want to share you some practical use cases. How can TALP be used? The different use cases that I'm going to show are listed here. And the first one is the easiest one. The easiest one where we can get the metrics without doing almost anything. We just need to export a couple of environment variables. If you have TALP installed in your machine, we tell DLB that we want to use TALP with this flag, and then we preload the library and we run our application. With this, without touching anything in the application, without doing any other configuration, we get the metrics at the output. So our application runs, TALP gathers the metric during the execution, and at the end, at the very end of the execution, we get the summary of metrics of how my application performed. But if I know my application and I know that it has different regions and I want to obtain a more detailed, and I'm very happy of how TALP works, then I want to have more information and understand if the efficiency is being lost in one region of the code or another. Then I can annotate my code, so I can use the TALP API to annotate the code with regions. This means that I can mark one part of the code. We call them monitoring regions. We register a monitoring region with a name, and then we can start and stop whenever we want, and we will compute the metrics just for this part that I'm monitoring. What I will get if I do this and I run the same way that I was showing before, I will get an output like this one. I will get the output for the global region, the same one as the one before where I do nothing for the whole run, but I also get metrics for the different regions that I have annotated on the code. And also note that, for example, in this region that we call kernel computation, we don't have MPI parallel efficiency metrics because in this region, in this part of the code, we don't have MPI calls. So every region will show just the metrics that are relevant to it. The same thing as the GPUs. In this case, there were not GPUs in this execution, so the GPU metrics do not appear here in the output. So every region will obtain the metrics that make sense for that region. The other use case that we have is a bit more advanced, is to get the metrics at runtime. So if we are able from our application or an external resource manager to obtain these metrics, we will know if this execution is being efficient or not and take decisions at runtime before finishing. In this case, we have the same situation as before. We have the application, the MPI calls are intercepted, and TALP gathers its metrics, but we have an additional API that is used to obtain the metrics. So the same way as before, we register the monitoring region, and then from this data structure, we can obtain the different metrics. This enables us to take decisions at runtime. And one use case that we did is to integrate TALP with one application that it's called Alia. And Alia was getting the metrics from TALP and deciding if the metrics were not what Alia wanted or what it was coded that were the target efficiencies, it will change the number of resources that it was using, either increase it or decrease it. You can see in the plots, in the x-axis, you have the different time steps. And in the y-axis, in red, in the left-hand side, you have the communication efficiency, and in the right, the number of cores that corresponds to the blue line. In this case, the red bar here marks the target communication efficiency, and at the beginning, the communication efficiency was below the desired. We see the red line is below the red bar. So at this point, Alia decides to release some resources and work with less resources because the communication efficiency is lower than it wants. So we reduce the number of resources. We see that the communication efficiency improves, but still is not reaching the target. So we release again some resources. And at this point, with this new number of resources, the target communication efficiency is reached, and we stay here. If we in the other plot, we see the opposite situation. So the communication efficiency that we were measuring, which is the red line, was above the target one. So at this point, Alia decided that it can use more resources because the communication efficiency is very good. So we increase the number of resources that we are using. We see that the communication efficiency gets worse, but still above the target one. So we will increase the number of resources until we get to the target communication efficiency at this point with this number of resources. So this runtime allows us to take this kind of decisions while we are running. The other nice thing that we have is the integration with the continuous CI/CD frameworks. And the idea is, okay, we do some developments, we commit our work, we run the correctness test, and then we run the performance test measuring the metrics with TALP. And based on what we get from here, then we can plan to roll back the changes or to plan the new developments. There are two visualization modes that we have with TALP pages. One is a scaling efficiency. So for a single commit, let's say you run different cases, and the other one is the metrics evolution for different commits, how the metrics evolve during the different commits of the code. This is the output that you would get with the scaling efficiency. So this is, again, one commit, one version of the code, and we obtain all the different metrics, and we say, okay, this specific case, we want to run it with this configuration. For MPIs, 56 OpenMP processes. For MPIs, 56 OpenMP. For MPIs, 112 OpenMP processes. With these three configurations, we get the metrics and we see how this version of the code is performing regarding the different metrics. The other visualization is the metrics evolution. In this case, in these plots, every dot you see is a commit. So here is the timeline, and the dots is when I did a commit in my code. And we can see the different plots in this one is plotting the elapsed time, this is the useful IPC, and the bottom one is the parallel efficiency. So between this commit here and this commit here, we did an improvement that reduced the elapsed time. So this is good. We saw that the execution time was reduced. And checking the other plots, we can observe that the execution time was reduced because the parallel efficiency increased. This allows us to check for the different regions, because in this case also we have regions, and here with clicking on the different regions, here we just enable 3 of the regions, but you could enable the other ones to check how the other ones are performing in this case and in every different commit. So, as a summary, TALP is a lightweight tool that gathers efficiency metrics. It can gather them at finalization, and this allows to do the continuous performance monitoring to see how your executions are performing. And it also allows to gather the efficiency metrics at runtime. That allows us to take some decisions at runtime, even abort simulation, because its efficiency is very, very low, for example. The nice thing is that its low overhead allows to use it in production runs. So you have your production simulation that you want to run, and you can run it with TALP and get at the end if how well you're using the resources to know if you can scale one step further, for example. We don't store a lot of data because we are gathering all the data during the execution. And we also provide an API to annotate regions, that this helps you to understand which part of the code is losing the efficiency. And the idea is to get all this information that we gather from TALP to decide when we need to do one step further and do a detailed analysis, because this is just giving us some metrics or indications. At the end, it might need to do a detailed analysis using traces. As I said, the current version is this one. It supports the MPI metrics, the hardware counters, and GPU metrics for NVIDIA, for NVIDIA devices using CUDA or OpenACC. The GPU metrics for AMD are under development, and we are also working on getting the computational metrics for the GPUs. And the OpenMP metrics, although they are implemented, we are still under testing and trying to finalize some of the metrics, how they are computed. Here you have all the links to download DLB. We have installed it already in some of the EuroHPC systems, in case you are interested. And so we did this beta version really quickly for this webinar today, so that we have everything ready and you can start testing it. That's why the documentation is not so up to date. So please, if you get it and you find any problem or you have any question on how to install, how to use it, write to us and let us know, because maybe the documentation is what is not so up to date. But all the GPU metric support has been quite tested, so we are quite sure that it works well. And that's the end of the presentation. And now, if you have questions or comments, I will be happy to answer.